Okay. Hello everyone. Just wait for 1 or 2 minutes and then we'll start. Okay, let's start now. Good afternoon. Are you guys able to hear me?
Good afternoon. Yes, we can hear you, sir. Yeah.
Okay, excellent. Okay, so we did work till here, and let's see. Okay, so an update on your quiz. Um, I saw that most of you did reasonably well, and the quiz was out of 40 marks, so there were 40 questions with 1 marks each, and the average was around 14, and the highest was 25. Most of you were in that 14, 15, 16 range. So it seems like you do have some knowledge, reasonable knowledge of semiconductor physics. But we will do a quick recap anyway, and I'll emphasize the stuff that I found a bit lacking in the quiz. Today we have a tutorial from 6 to 7. As I said, we'll try it on Saturdays initially. In the tutorial, the TAs will be discussing the quiz and the solution, and you can self-evaluate at that time. Okay, let's start. So the way I'm planning to work on this course is I'll go from the very basics, but I will not spend enough time on the basics, and slowly but quickly go to that the MOSCAP and the MOSFET stuff, because that's the primary focus of this course. I will spend today's session and maybe the next week's session a little bit on this. So let's see. So semiconductors, you all of you know, has a conductivity somewhere in between insulators and conductors. And I've shown some examples here, some materials and a range of their conductivity. So let's start with defining the various semiconductor parameters and the things that will be important for you throughout this course. The first thing is, oh, just a minute. Okay. Sorry. Is it okay if I use this view where you can see everything on my screen? Because I might need to go back and forth between the meeting screen and the presentation. Is this okay?
This is fine
Yeah.
because in this Google Meet we can change the layout where it is maximized.
Okay, excellent, excellent. Right, so we'll start with intrinsic semiconductors. So we in this course will be primarily discussing silicon, but a lot of the discussions that we will have are also valid for other semiconductor materials. They usually share similar properties, and that is the reason of their semiconducting nature. So this on the right, top right, you can see is a representation of the silicon crystal, the crystal structure. And if you can figure out, I have shaded this with blue to show that each silicon atom has four nearest neighboring atoms associated with them, right? And let's see, what can we talk about? Yeah, so this is that, and then there's something called which will come in handy when we go to advanced devices, is the crystal plane or the wafer planes. So let's see if I can draw on this. Oops. Yeah. Just a minute. Okay, let's see. Oh, different subject. Okay. X in this direction. Oops. This is X, Y, Z. So I'm trying to draw the rough outline of this block here, and this plane that I'm shading right now is essentially one of the crystal orientations that I was talking about. What are the other options? Let's just quickly look at that. The other options are is this plane, which is this diagonal. If you can imagine this diagonal, right? So this plane here, all throughout like this. This diagonal is another, and then finally you have zx, sorry, x, y, z, and then you have sorry for the weird cube. It's this plane here. This one, this one, this one. So if you can imagine this triangle inside this, this is 111. So these are the crystal planes. The wafers are usually cut along one of these planes. The most common is 100. And usually when the wafers are cut, they have some form of a, these are like discs, but they usually have some form of a notch here. It's not like a, oh, it's not really, we can't probably make this out. Wait. So this is, if it would have been a circle, and then they have a notch here like this. So the notch is usually used to identify the coordinates of each die, and they help automate the fabrication because it provides a reference point. Okay, let's move on to other stuff. Wow, using this PPT for drawing and all is really tricky. Not used to this. I usually use this other tool called this Microsoft Whiteboard. But let's see, let's try this. Okay. So a few things to note. So the silicon crystal it's a 3D crystal where the atoms are around 0.5 nanometers apart, roughly, of this order. And that would imply, if you use this to calculate, it would imply that there are approximately these many atoms per centimeter cube. Yeah. So how is this lattice held together? If you remember from your school level stuff, usually these silicon atoms are bonded to the neighboring atoms. As I said, there are 4 nearest neighbor atoms for silicon. So these are the bonds where there's charge sharing happening between these atoms. So there are electrons involved. Each silicon in its outermost shell would have 4 electrons, if you remember the periodic table. So they'll have 4 electrons, and then they're bonded like this. So at 0 Kelvin, which is the absolute zero temperature, all of this is held into place and everything is nice and stiff, and there's almost no movement because there's no energy. But as you increase the temperature, what happens is there's thermal energy associated with all of this, and that thermal energy results in these atoms jiggling about, and there's a lattice vibration. Okay, it depends on the temperature, of course. So higher the temperature, the more the lattice vibration, the more thermal energy there is. And if you go to reasonably high enough temperatures, the thermal energy is sufficient to break these bonds here. So it can break bonds and create what we call free electrons. In the strict sense of the term, they're not really free electrons. In physics, usually free electrons means electrons that are free in vacuum. That is, there is no other potential field that they're going through, and there are no other external sources of electric fields that may affect them right now. So they're a sort of free. In this case, the electrons are still in the lattice, they're still in the semiconductor material, they're not in vacuum, but then they're free from the bonds, right? So they're free in the sense that they're free to move. And these electrons would in turn result in what you normally see as current. Okay, so this brings me to this other point. What are the mechanisms of charge flow in these materials? So there are usually 2 mechanisms of charge flow. Can anyone tell me what those 2 mechanisms are?
Drift and diffusion.
Yeah, no. So I'm usually so drift and diffusion will come to it later. What I'm talking about here are the first mechanism of charge flow is through free electrons that we just discussed. The other mechanism of charge flow is through bonded electrons. Now tell me, how can charge flow through bonded electrons? Anyone?
Whole
Yeah, bounded means one electron will be in the bounded electron. It's bounded electron means it's in the bounded atoms. So I think when the electrons will jump from one to one other place, means in between the atom, so there will be vacancies created in the bounded in the atom, in the bounded atom. In the free electron means it will be like out of the electron, means in the atom. So which is the free, which is in the like in the valence band.
Right, excellent. So these free electrons, as I said, valence band, will come to valence band later. So these free electrons are essentially not a part of this silicon-silicon bond, so they are free to move around. So if you apply an electric field or something, they'll move. So there's this flow of electrons. The other is these bonded electrons, where say if I break this bond, so I am left with say this silicon, and this electron has become free now. So there's this vacancy over here where this electron used to be, but this neighboring silicon atom still retains its electron. Suppose it's a very crude picture, but say this jumps here, so you will be left with a vacancy here, and then from the next one this can jump here, so the vacancy will come here. So the bonded electrons are sort of jumping from one silicon atom to the next, and in turn there is a movement of the vacancy from one silicon atom to the next in the opposite direction. These vacancies are basically absence of electrons, so obviously we call them holes because it's a hole where there's no electron, right? And they are positively charged. Right, so that's the other mode in which charge flow can occur. And when we talk about current in these devices, what is current, by the way? Can anyone tell me what current is?
Flow of electron per second.
Right, in this case. But in the general sense, it's any flow, right? Any directional flow is current, right? So for semiconductors, we are, as you said, is the flow of any charge essentially, right? Because in most of the cases, for ease of understanding, we'll be talking about electrons and holes, not in terms of free and bonded electrons. Although all of the flow is through movement of electrons, we'll still treat them as two separate, sort of like two separate particles, electrons and holes. And so the flow of charge is what the current is. Okay. So in all of these intrinsic materials, that is what we have been talking about so far. If I denote the volume concentration as Ni, so this is the volume concentration of say electrons, and I denote the volume concentrations of hole by say P of I, this is for holes, this will hold. Okay, so I can show that Ni is equal to Pi. Can you come up with a reason of why it must be so?
Yeah, as much as the electron will be jump like it's in the freeze, that much of the vacancy will be there. So it will be equal.
Right, because the electron is being the generation of this electron is happening from the silicon lattice, so there must be a corresponding vacancy that the electron is leaving behind. So whenever there's an electron generation, there is a hole generation as well, so the numbers are the same. So the approximate value for this at 300 Kelvin, which is what we usually consider as room temperature, is around 1.45 10 to the power 10 per centimeter cube. So for most of the practical numericals and all of that, you can just assume this to be approximately 1 into 10 to the power 10. Okay. So that's one thing. Also, I wrote 300 Kelvin specifically because this number changes with temperature, and it's a very strong function of temperature. Why?
Yeah, because as temperature increases, that vibration will happen, more number of electrons will break the bond.
Okay, excellent. So that's the correct reason. And here's something interesting about this. Compare this number with the number of silicon atoms there are in the crystal. So in one of the previous slides, I said that the number of silicon atoms is of the order of okay, whereas the number of electrons or holes generated is of the order of 10 to the power 10, which means, first of all, this is too less compared to the number of atoms. This is too less. It is almost like what is it, 10 to the power 12, so almost like 2 out of 1 into 10 to the power 13. So there are 2 electrons for every 10 to the power 13 atoms, that sort of a thing, right? So that is actually too less. And that will bring us to something we call the doping. Again, we'll come to that later when we discuss extrinsic semiconductors, because this number of electrons is first of all not enough for our devices. We want the devices to carry large currents and everything, so we want there to be more electrons. Let's see, someone told about valence bands and stuff, so we'll briefly discuss about energy bands. So you must have seen this picture where we draw energy bands, something like this. You must have also encountered this during the quiz. Right, something like this, where this is the electron energy. This direction is usually the geometrical distance. Right, so this is conduction band, valence band, band gap, and all of that. Okay, and we say that free electrons are in the conduction band, the holes are in the valence band, and all of that stuff. Now, say I know the energy of a free electron. Say I have a free electron, the energy of it is E. Can you tell me, just from this information, what would be the potential energy of this electron and what would be the kinetic energy of this electron? Say this is the band gap of the material in which the electron is in. Anyone?
E by 2 maybe.
E by 2 is what?
Like potential E by 2 and kinetic E by 2.
No. Okay. So what is band gap here? Do you know what the band gap means?
Energy difference, right? The amount of energy required from moving from valence to conduction band.
What is valence band? What is conduction band? Why does someone need to move from one to the other?
Um, to basically start the conduction.
So can't we conduct in the valence band itself?
The space will be more in conduction band.
Space is not a problem because you're still in that same silicon lattice, right? So the space is anyway same. It doesn't matter. Okay, think of it like this. Remember the lattice picture we were talking about, where there were bonds and then this bond broke and this electron became a free electron. So obviously when there's a bond, right, it is existing in almost everything in nature wants to stay in the minimum energy state possible, the minimum energy state it can achieve. So if there's a bond, it means that it is in some sort of a potential minima. It is in the minimum energy state possible. Now you're applying, say, some sort of energy to it, say thermal energy to it by increasing temperature or something. And the bond will only break whenever you provide sufficient energy so that the electron can break this and go to the free electron state. So there is always a threshold associated with this. Okay, so in a way you can think of this band gap as that threshold. In a way, it's not exactly that. I'll tell you what the band gap is and where it comes from. So this EC denotes the minimum energy required for a free electron to exist. So in that silicon lattice, the minimum energy that a free electron must have is this EC. So that means that for an electron to be a free electron, there is this threshold of EC that it needs to have. So the energy cannot be less than EC. Now, if it has an energy, which is say somewhere here, which I denote by this E, then EC is the potential energy of that electron, because it's this sort of minimum threshold energy that the electron has to have. Okay, it's a consequence of the lattice structure and the confinement that the electron is in. Anything other than EC, anything extra that this electron may have, is essentially the kinetic energy. Okay, so it is okay for the electron to move and expend this kinetic energy, and it will then just fall back to EC. That is it. Okay. Okay, let's see. Some other stuff, band gap, silicon band gap, just numbers so that you have an idea, is 1.12 eV at 300 Kelvin normal. Band gaps are also used to classify between materials. They're used to classify between semiconductors, conductors, insulators. Insulators have a large band gap, so it's very difficult to free electrons in insulator lattices. Semiconductors have a reasonably smaller band gap where room temperature can see some electrons come into play. Like we said, 2 out of 10 to the power 13, that sort of range is what we are talking about. Metals have an even smaller band gap or almost non-existent, so that there's a lot of electrons, free electrons, coming into play at room temperature. So that's where the conductivity difference and all of that comes in. Why am I writing at 300 Kelvin? Probably because band gap is a function of temperature, right? Can you guess what sort of variation would it have with temperature? Would it increase, decrease? Any idea?
It would decrease with temperature.
Why?
Because as the temperature increases, the lattice vibration more increases, and the electrons gain more energy to jump to the conduction band.
So the band gap would
Decrease.
right. So if at say 0, my band gap for silicon is somewhere over here. It is somewhere close to 1. I would say 1.7 or something. I'm not exactly sure. Somewhere around this range, 1.17, 1.18, that range. 1.175, I think. Okay, at 300, it is around 1.12, like I said. And then as you go higher, it decreases. The decrease looks something like this. Okay, so just to give you an idea, if you go up to say, if this is say 600 Kelvin, okay, this number would be around 1.02 or 1.03. So it's not a lot of decrease. As you can see, it's a very slow decrease, but there's a decrease nonetheless. Other materials have almost similar curves, but the slope might be different. So for gallium arsenide, it would go something like this. And then for germanium, it's more like starts off at a lower value and it goes something like, oops, like this. So let's talk a little bit about this, the conduction band, valence band, and what we know as the energy band model for these electrons. So let's see, the reason there is a band gap and then there are bands of valence and conduction and all of that is because if you remember your school level physics, a little bit of maybe quantum mechanics or a little bit of school level chemistry, you would remember that usually there are states associated with anything. So in quantum mechanics, if there is a confinement, say a particle in a well, the most common problem, if there's a confined charge here, it can only take certain energy levels, right? So for atoms, there's a very highly charged and heavy nucleus. So the potential profile would look something like this for an electron. Okay, so it wants to stay as close to the atom because as close to the nucleus because the nucleus is attracting it. So for an electron, it's basically the lowest energy. It wants to go towards the nucleus as much as possible. So this is a very restrictive confined system. So in that, there are certain energy levels that the electron can take. You would have studied this in the if you remember the hydrogen model with this shells around the nucleus. If you remember this picture, that there are shells that the electrons can be in, and then there are defined radius for that cells which you can calculate. You have to equate the forces and all of that and calculate the radius. So essentially what that means is that there are some defined energy levels that it can rest in. Now if you have a single atom like this, say these are the two energy levels in which the electrons can stay in. So these are all bonded electrons, okay, in some way bonded to the atom. Actually, even if it's unbonded, it has to be in one of these energy states. So even if it's unbonded, it will be there. Do you remember these things? You had these electrons with energy, they go from one to the next, and all this sp, d, f, all of that. Do you remember from school chemistry?
Little
Yes,
bit.
sir.
Yeah.
Yeah, right. So these are the levels, right? So if I start bringing two atoms, so these are two identical atoms, say silicon atoms, okay? These are one of the two energy levels in which electrons can rest in. So I have some electrons here, I have some electrons here, okay? And they will follow what is called the Pauli exclusion principle. All of this is not necessary for a MOS device physics, but just to give you an idea. So say I start bringing the silicon atoms, individual silicon atoms close together so that now they start bonding, okay? So this is the distance between the atoms. I am reducing the distance in this direction, okay? What will happen is, initially, both the atoms will have the same energy levels because they are exactly the same atoms. Now, as they start coming closer together, the atoms will start interacting with each other. Earlier, an electron in silicon atom A was feeling a force because of the elements in silicon atom A. But now as they're coming closer together, it's also feeling a force because of the silicon atom B. So the energy levels will reshuffle and they will split into multiple energy levels to accommodate all of these electrons. Okay. So what happens is they start looking something like this. So after a certain threshold, if you bring them closer, they will split like this. Something like this. So these are the energy bands. Okay, it will split into multiple bands like this. So instead of drawing all of that, I'm just shading where the electron bands are, where the electron can be in. So all the shaded region is where the electrons can be in. Okay, so as you can see, at the 0.5 nanometer spacing for silicon atoms, silicon crystal, there is actually a region here where there is no energy state favorable for the electrons to be in. And that is the band gap we are talking about. Actually, what happens is, if you just have two atoms, no? If you just have two silicon atoms, these bands will split into these two levels here. But in a silicon crystal, you will have multiple silicon atoms, again 5 into 10 to the power 22 per centimeter cube. So all of them are interacting with each other, and so the bands will split into a large number of sub bands like this, and they will be so close to each other, they'll be separated by so small an energy that for an electron this would almost look like a continuous band of energy. Okay, because the electron at room temperature has enough energy, thermal energy I mean, to go from one to the next. It is almost negligible. The separation between them is almost negligible. So it looks like a continuous band. Again here, it would again be a continuous band. So when the electron is flowing, it is actually flowing from, you know, one atom's band to the next and all of that. It can go in energy in this, anywhere in this, based on how much energy you apply and all of that. So this is EC, EV, and then there are higher order bands here, and then there are bands here, and so on and so forth. So that's the band picture, but we don't need to get into more details than that. Any questions on this? No? Okay. So let's see. The next thing I wanted to talk to you about is the flow of electron and holes, which we have already done. So I'm just going to go quickly over it. So whenever we are drawing energy bands and all, you know, we usually draw electron energy. So electrons are negatively charged. So in the band diagrams we draw, if the band is like this, the electron will actually go like this in this direction, would want to go in this direction, because the bands are drawn with respect to the electron, right? So this is a lower energy for the electron, this is a higher energy for the electrons. It will always try to go in this direction. So it's very easy to think of it as some sort of, you know, liquid or fluid or something, you know, like sand or water or something that just flows down this. Okay, it's very intuitive that way. For holes, however, which has the opposite sign, they tend to go up like this. And so one analogy that I always keep in mind, which helps me, is I always think of electrons as some fluid and holes as the bubbles in it. So if you imagine this sort of a bottle, which is like half filled with some fluid, if you tilt it in this direction, you know, all of your fluid will come here. So the fluid has essentially flowed in this direction. and the holes, which is the air gap or the bubbles, have actually flown in the opposite direction. It has gone up. So you can keep this analogy in mind. Okay. We now come to this next topic of effective mass. We have discussed so far, just a quick recap, intrinsic semiconductors. We have discussed what the energy picture is. We now come to effective mass. You would know this, that all electrons will in essence have some mass, right? They are, I mean, call it particle, call it wave, whatever it is, there is some resistance to force there. There's some concept of inertia, so there's some mass associated with them. Essentially, it means that if I apply a force on an electron, I can always write it as some constant times the acceleration. So this constant is what I call mass. That's it. Now, effective mass is something different. So if you remember in the beginning of the lecture, I said that these are not in the strict sense free electrons, like they are not in vacuum. They are still in the silicon lattice. So they are being acted upon by internal forces because of the various silicon atoms and other electrons and everything that is present in the lattice. Okay. So in a sense, if I apply an external electric field or something, and somehow imagine I'm applying a force on these electrons. So the net force on an electron, I can write it as whatever external force that I'm applying plus whatever internal force there is. Okay. And this would be equal to the mass times the acceleration. Okay. Now these internal forces are very difficult to calculate. You know, there are so many atoms, so many nucleus, so many protons, electrons, and all of that stuff, and these electrons are also moving and scattering and changing directions willy-nilly. It's very difficult to track all the forces as a function of time on a single electron and then do that for all the electrons, and everything is very tedious and almost impossible that way. So a quick trick that we do is we imagine that assume this is 0. Now if we do that, if we say internal forces are 0, whatever we use, you know, this function f external equal to this equation equal to ma, if we use this to calculate something assuming this internal force part to be 0, the answer is not going to be accurate. It's going to be wrong because this is a very significant part of it and we have ignored it. So what we do is we say I will change this constant so that my answer is accurate again. So whatever error is coming into play because of this assumption, I will compensate by changing this constant. So then we write where m star is what we call the effective mass. It is the mass of the electron taking the whole semiconductor system effectively as a system where there is no internal forces. So all the contribution of all the internal stuff is included in the effective mass. That is why this becomes a material parameter. So the effective mass will be different for different semiconducting materials because their internal forces are different. Is this clear?
Yes, sir.
Okay. It also makes the calculation easier actually. We don't have to go into calculating all the forces and take into account all the errors and stuff. It actually makes it easier. Just so that you know, if the electron is truly free, we can represent the energy something like this. You might already know this. Okay, this is the electron rest mass anyway, and this is the Planck's constant h by 2 pi. This is called the wave number. This is the energy. So this is how we represent. It's nothing but P is for momentum. Writing it. Momentum squared by 2m. Okay. So this is just an aside, just for your information. And this would look, it's a parabola, right? So it would look something like this. This is the KE. And from this, for a free electron, we usually calculate effective mass as for a free electron, we usually calculate effective mass as 1 by h bar square. This, because you can see that if I apply this idea to this equation, I will end up getting m naught. Right? Imagine this. This is differentiation of energy with respect to k. If I do 2 times differentiation, it would lead to basically h square by m naught. And I divide it by 1 by h square. So I'm left with 1 by m naught. And if I take the inverse of that, I will just get m naught. So m star equal to m naught for a free electron. Same thing. However, for an electron that is in the lattice, that is not really free, the energy will not look like this. It will look like some weird shape like this or something. But since most electrons usually like to stay, and actually most things in nature like to stay in the minimum energy point, they will usually be located around here. And for all intents and purposes, if there's any curve, I can always zoom into this minimum energy point and say, well, I can always approximate this to be a parabola, some form of a parabola. And then if I use this formula on this curve, at exactly this location, whatever this spews out is my effective mass. And that's usually valid. Okay. The next stuff is density of states. This density of state stuff is the last thing I'm going to talk about today, because we have like 10 minutes more. So this is the key idea behind this. I said there are multiple, you remember the atom coming closer together and the energy level splitting up into 2 levels, and then there are multiple atoms, so they each have split up into multiple levels, and then they create this band that I was showing, and the individual levels are so close to each other that there's almost no energy separation between them, and then they form a band like this, the thing that we discussed a few slides back. So what we can do is, in this conduction energy band, if I try to find out, I can do this. Say I take this much energy gap, this energy window, this delta E, and I say how many energy states are there in this delta E window. So I can do some calculation and I can find out that, okay, there are this n number of energy states in this delta E window, and then I can do the same at this energy, at a delta E around this energy level, and I can find out, okay, it's something else, or maybe it's the same, I don't know. So we can always figure out how many actually states there are in at any around any given energy, and we usually calculate this and then per unit volume. Otherwise it makes no sense, because the larger the crystal you consider, the more number of atoms you consider, the more number of states you have, so it will go on till infinity. So per unit volume, I have a fixed number of atoms, that means, so say per unit centimeter cube, I know I have 10 to the power 22 atoms of the order, right? So per unit volume at this energy, around this energy, how many states are there. Okay, that is essentially the density of states. What is the density of energy states per energy per unit volume? Now, why is this important? Because the electrons can, since they can only occupy these available states, it becomes very important to find out how many available states there are. So say if there are 10 available states, that would mean that there can only be 10 electrons in this. Say in my whole EC, there is only 10 states. So I can only have 10 free electrons, which is not very much. There won't be any discernible currents, right? So that's the whole idea behind density of states. Now, for a 3D semiconductor material like silicon, for what we basically use for MOSFETs and everything, this density of states comes out to somewhere around it's obviously a function of energy. It comes out to be somewhere around this number. Oops. Okay. Here Mn is the electron effective mass for density of states. Actually, since the effective mass is sort of this approximation we do to make our calculation easier, we use different effective mass for different calculations. So we have a what is called a conduction effective mass, which is used for calculating the electron movement and transport. And then we have a density of states effective mass, which is used for calculating density of states for all the electrostatic stuff. Similarly, for the holes, it would be, I mean, for the valence band, it would be something similar, but the effective mass will be replaced by effective mass for holes. Okay. So if I actually, this is a very common picture you might find in books. In this direction, I'm plotting the density of states. In this direction, I'm plotting energy, right? So if this is my EC and this is my EV, the density of states would actually go something like this. Root over X. Yeah. So it's root over energy. So it will look something like this.
Question.
Yeah, yeah.
So you said like there are let's say there are 10 states which has 10 electrons, right?
Mm-hmm.
So I mean one state cannot have multiple electrons, you are saying?
No, so there's something called this, which prevents a state from having multiple electrons. So imagine these states to be like there is a degeneracy, so it can have multiple electrons, but that number is fixed. So it can only have, so one state accommodates one spin up, one spin down electron, something like that. So, but it can't go more than that. So imagine these states like chairs or seats, So only one electron can go and sit in one chair. So the chair is filled. So another electron can't sit on it. So it has to go to another chair. So how many electrons you can move to the conduction band, which can effectively give you current, will be determined by how many states you have available.
Okay.
There is one other thing that determines how many electrons that can be in the conduction band. One is obviously the density of states, which is how many states there are available. The other thing is what is the probability of that electron sitting in that chair or going to that state. See, we know that the natural systems again go to the lowest energy state. So if I have a state available at very high energy, it is not a very favorable state because the electron is most likely not going to go there. The probability of it getting that much energy to go to that higher state is probably not much. So it is not going to be filled. So it is important not only to have states, but to have them at a low enough energy so that the electrons can actually fill them in our normal temperature range where the devices are going to be operated. Okay, so it's 2:57 now. I'm going to stop here. I have 2 or 3 minutes more. If you have any questions, feel free to let me know.
So there is confusion between Pauli exclusion principle and Schrodinger wave equation in that sense. So what Pauli exclusion principle says, two charge carrier cannot occupy same state, right? And what Schrodinger wave equation says, every state can be represented as a state itself, right? So aren't they contradictory, or they are the same thing?
I did not understand your question. I understand the Pauli exclusion principle that you said. What did you say about Schrodinger?
We can represent each particle as a available state. This is what Schrodinger wave equation says, isn't it? Or my understanding is not correct?
No, the Schrodinger wave equation essentially gives you, in terms of energy state, it gives you all the possible energy states that a particle can take. That is it. It does not specify anything about how many particles can sit in one energy level. Okay, so if I give a potential profile, any potential profile, say something like this or any shape where a particle can be kept, it will just tell me what are the energy states available that the particle can take, and that is it. The Pauli principle actually says how many particles can sit in one state, what is the maximum number I can accommodate per state. So they are not the same, they have to be taken together to calculate this stuff.
Okay, sir. Thank you.
So the Schrodinger equation gives you the chairs. The Pauli exclusion principle will tell you how many people the chair can fit. That is it. Okay.
Okay, thank you, sir.
Okay. Okay, then we'll stop the class here today. And I want to take a quick feedback from you. This was the first lecture of this MOS device physics. Although we didn't go into MOS physics yet, tell me, what do you think about the pace of this class and about what I'm talking about right now? Is this helpful in any way? Do you guys already know this? Do you want me to go faster or slower, more in depth or more, faster, skimming the surface? What is going to be useful for you?
Look, I think covering these all will be surely helpful. A little bit of device physics also will be surely helpful in understanding MOS physics on a later stage.
Yeah, so what I'm doing right now, you'll actually be using some of these equations while deriving stuff for the MOS physics. So that's why I'm going over them quickly. Yeah, but any comments regarding the pace? Is it okay for you?
Yes.
Okay.
Yes, sir.
Yes, we are fine with it.
Okay. At any point of time, if you feel that you already know something and you want me to move on, or if you feel that you want me to slow down or speed up, just let me know. Okay. Let's have this sort of an informal thing, especially on, and I don't know about your other instructors, but for this course, you are always free to just stop me midway and speak. Okay, and we'll go through this together. Thanks everyone for attending.
Sir, I have one small thing. Sir, this
Yeah.
regarding formulas and all, you want, we want to be, is it needed to be memorized? Anything for the? I'm just asking for the examination point. Is it for the examination point? How much we have to be more concentrate on this formulas and all?
So from the exam for this course, I would suggest don't memorize anything. Okay. If there is any question that requires you to use a formula, I mean something that is not obvious, for example, pi equal to ni, the thing that we discussed today is a very obvious thing. Apart from that, if there's any big formula or anything that you need for the exams, I will mention that in the question paper. I'll give you the formula, I'll give you all the numbers that you require, say the intrinsic concentration and all of any number that you require, effective mass, and all of that I will give you in the question paper. So you don't have to memorize anything. Just understand the concepts and you apply them when you solve the problems. That's all.
Thank you.
And reference books that we have to refer.
Okay. So when I'm teaching this, I am following multiple books and some of my own knowledge from working in this field. If you want a specific book, then you can take up any book on MOS devices. I'll give you some names. One is, say, that there's a good book by Cividis, if you know about it. It's called Operation of MOS Transistor or something. There is a book by Neiman. There is a book by SMZ. What I'll do is I'll send you a list of books that might be helpful for you through email, and you can choose any that you want for your reference. Okay?
Okay.
Thank you. Thank you, everyone.
Yes, thank you.
Yeah, thank you.
Thank you, sir.
Thank you, sir.